more or less skip over 2 equations and 2 unknowns, but let's just do one. 2x plus y equals 6, and x minus 2y equals 4. Okay? Now the geometry of this is we can graph this equation. We can graph this equation. You can see from this form that the y-intercept is 6, and the x-intercept of this is 3. So the first equation does this. So this is 2x plus y equals 6. You can see from the form of this that the x-intercept is 4, and the y-intercept is negative 2. So naturally, where I wrote the 3 is right where I need to run this line. Now it's 2, isn't it? Okay, it's 3. Okay, so there's the line. I didn't hit my 4 very well. And it's a hand-drawn graph. So where is this point of intersection? Well, the way I drew it, it looks like it's at about 3.3. Now, if I'd have gotten the line up a little higher, it might have been closer to 3.2. So I'm going to estimate that this point should be at about 3.2. And over here, it'll actually be a little higher than this, but if that's negative 2, that's about negative 0.8. I'll say negative 0.7. Now we can check this. We substitute it into this equation. 2 times 3.2 plus negative 0.7 should equal 6. I don't expect this to come out exactly correct, but it's close because it comes out 5.7 equals 6. So that's pretty good. Okay? And we check in the second equation, and we see that we get 3.2 minus 2 times negative 0.7 equals 4. Well, this is 4.6. Okay? And that's just not, I would call it pretty good, but it's not too awful. Right? Okay? So we know then that the point is somewhere around these values. Now we could start adjusting these values a little bit and see how that affects what we get on the left-hand side in each of these, and maybe get some numerical intuition that allows us to approach this, but boy, that would be tedious and not particularly profitable. So what we do is we solve the system. Okay? Now one way to solve it is solve this for y, and then plug that in for y here. That's substitution. We don't do that in this course. Okay? It's linear algebra. Everything's linear. We do elimination. So we take this equation and we double this equation. Right? And now, actually I'm going to multiply by negative 2 because I want to be able to add these. I don't like subtracting. And you shouldn't either because it's too easy to make errors with negative signs. Even though at one time my clerical abilities are pretty good and I could kind of get away with that. Still better to change the signs here and then add. Okay, so we get 5y equals negative 2, so y equals negative 2/5. Okay? And I don't want to use decimals because then you get tempted to round them and you get errors with what we do in linear algebra. Okay? And then we plug this back in here. And this, running around here, it gives us 2x plus negative 2/5 equals 6. multiply through by 5 to get rid of denominators. We get 10x minus 2 equals 6. 10x equals 12 makes no sense at all because I didn't multiply 6 by 5. That's 30. That's 32. So x is 3.2. So actually I kind of lucked out on the 3.2, but I didn't get a very good estimate on this. That should have been like 0.4, but the way the graph is drawn sure doesn't look that way now. Okay, but if I had hit the 4, I'd have had a little lower estimate here. So, and 3.2 is 32 fifths, and I probably should have written 32 fifths, but it's not 32 fifths, it's 32 tenths of 16 fifths. Okay? Keep an eye on me, I don't always catch those things. Okay?
It's okay.
Got a pretty good night's sleep last night, so I've got a 50-50 chance of catching each one. So far, I'm on a roll. Okay.
All right.
So that's that. Now you see the geometry of this. Okay? Now if I have 3 equations and 3 unknowns, and I'm not going to actually solve the thing because you all know how to do that. Okay? Then what would my graph look like? Let's say I got 2x minus 4y plus z equals 8, and 5x plus 7y minus z equals 4, and 3x minus 5y plus z equals negative 5. Okay? Well, the graph of one of these things is a plane in 3 dimensions. Okay? Three planes in 3-dimensional space. Okay? Now there are a lot of possibilities for those planes. They could all be parallel to each other with no common intersection point, just like 3 panes of glass in a doubly insulated window. Okay? Tilted one way or another. Not that you would do that in installing a window, but you could do that one before they're installed. So you could have that and you'd have no solution. There's no point on any one of these that lies in any other, so there's no set of values x, y, and z that makes all 3 equations true. Okay? Make sense? Just like over here, I could write 2 equations that have parallel lines. So if you do this, you end up not getting a solution. Okay? If the parallel planes don't coincide. Or the 2 lines could actually be the same, but maybe when you graph them, you're a little careless and they don't look like they're the same, and then you do the algebra and you find out they were because everything gets eliminated. Okay? So any x and y on one plane is on the other. So you have an infinite number of solutions, right? If these 2 equations coincided, if they were the same equation, then every point on the line is a solution. Okay? So you have 3 possible cases here. Lines are the same, lines are parallel but different, or otherwise they intersect. In 3 dimensions, what do you have? Well, you could have 3 parallel planes that don't have any intersection points, right? Or at least one that doesn't intersect with either of the other 2. The other 2 might even coincide, but if any 2 of them don't coincide and they're all parallel, you don't have any solutions because you don't have any x, y, z that lies on any one of those planes, on every one of those planes. There's no x, y, z that would solve the system, and you would end up with something. Okay, then we'll see how that works out rather quickly. Maybe today, we'll see. Or you have all three of them coinciding, or all three of them intersecting at a point or on a line. Say two of them coincide, but the other one is not parallel, then there's a line of intersection. Okay? Now, if none of them are parallel, then they'll intersect at only one point. Because any two of them intersect along a line, some line, and then the third one will intersect that line. And at that point where the third one intersects the line of intersection with the first two is your solution. Okay? So you want to see these things geometrically. The geometrical, two-dimensional, three-dimensional intuition kind of guides a whole lot of introductory linear algebra, and even beyond that. Okay, so make sure you understand that picture. Okay, well, these are not going to intersect. I mean, they're not going to coincide. They're not going to be parallel. Nothing's parallel to anything else. Okay? So if we wanted to solve these equations, well, we could call this equation 1, call this equation 2, call this equation 3. Equation 1 plus equation 2 gives you 7x plus 3y equals 12. Okay? And equation 3 plus equation 2 gives you 8x plus 2y equals -5. That figure's going to be a little bit steep. Okay? So if these three are valid, if these are true, then this has to be true. So any solution, x, y, and z, of these three is going to have to include an x and y value that solves these two, and any x, y value that solves these two is going to have to be an x, y value that solves this one, which means if we can solve this for x and y, we can plug that x and y back into any one of these and solve for z. Got a value for x and a value for y, we can solve for z. So we know this. So etc., then plug the solution into the first equation. Okay? Now I can write the process like so. I've got my equations. Okay. Then I add equation 1 to equation 2, and I use that to replace equation 1. So equation 1 is going to become this. Okay? So I can say this, I can kind of notate this by so equation 1 plus equation 2 becomes equation 1. And then equation 3 plus equation 2 becomes equation 2. Okay? And at this point, I'm going to leave the third equation alone. I'm not going to mess with it. Okay? Now what I'm going to do
is that negative 5 supposed to be negative 1, sir?
2 plus, where did I get that negative 5? Right, supposed to be negative 1 here, supposed to be negative 1 here. Not that see, I told you something.
That's okay.
Right down to the last number that my peripheral vision didn't quite see.
That's okay.
Yeah, I know it's okay. I declare that it's okay.
Okay.
But I'm glad you think so too.
No.
Not really okay. I just assume not make those little errors. But, okay, so now what I'm going to do is I'm going to write down the system again. Like this. Now what did I do? Where did this come from?
Equation 2.
Took half of both sides of equation 2. Why did I do that? Well, because now equation 1 is going to become equation 1 minus 3 times equation 2. Okay? So what do you get? Did it again where I caught myself. Okay? If you do the arithmetic, maybe I got it right, maybe I didn't, but that's what we do. And you see the advantage of having a 1 in front of the y here is that makes it easy to figure out what to do to eliminate y up here. Oh, well, now I'm going to I can also eliminate y here, can't I? Okay, now this is not the order in which we're ordinarily going to do this, but it's equivalent, okay? And we'll write it out a little differently, but we'll do it in order, okay? And in the usual order. There's nothing wrong with this order, just not the standard order. Okay, so now we're going to do, okay, well, we got negative 5x. Actually, I'm going to take equation 1 while I'm at it here and multiply that by -1/5. That'll be our new equation 1. And of course that solves for x. So we get -27/10. Okay? And don't worry too much about the numbers. Make sure you see the process we're going through them. Because I'm going through it kind of quickly. You should be pretty familiar with these ideas. Okay? So, not quite familiar with this formula. Equation 2, I'm just going to write down again. And in the next step, I'll add -4 times this equation to this one, which will eliminate x and give us the value of y, right? But I'll do that in the next step. I'm not going to do that now because I want to use this y to take care of this y. Okay? So I'm going to add 5 times equation 2 to equation 3, and that becomes my equation 3 now, 2. Okay? So 5 times 4x is 20x. Add that to 3x, we get 23x. That's going to take care of y. And then I got to add 5 times the -1/2. That'll be a -5/2 to a -5, giving me -15/2. Check my arithmetic. But for the moment, tentatively believe what I did. Now all I have to do is add -4 times this equation to this one, and I've got y. And I add -23 times this equation to this one, and I've got z. Right? So, this equation's got to be what it is because we've got a solution here. So, that's going to get rid of the x. I'm still going to have a y. And -4 times that's 108/10, which is -54. It's -4, yeah. It's 54/5. Okay? I'm going to keep it -108/10 because I got to add it to -1/2, which is -5/10. And I think I have 103/10. Okay? Make sure that makes sense. -4 times this is 108/10. That's -5/10. That gives me 103/10. But you don't have to do these in your head. And usually the numbers won't be that nasty. They're not all that nasty. They're not really that bad. It's pretty simple denominators. But then I've got to add -23 times this to this, right? And that'll take care of the x. And oh man, I got enough multiply 23 by 27. And but I will. Okay, let's see, what's the easiest way to do that? 30 times 27, everybody knows, is 810. And then we subtract 81 from that, and it's 789. 789. And then I got to subtract 75 from 789, and my chances of getting this right are pretty thin. But I get 714/2, but of course, that's going to be 357/5. Now, if I actually got that right, I'm surprised, but you get the idea. Okay? I might have gotten it right. Yeah. so it made sense, but my working memory is what it used to be, so I'm not gonna make any claims. Okay? Which means wherever these planes are, they meet at the point where the x-coordinate is about 2.7, y-coordinate is about 10, and the z-coordinate is about 76.4. So if you got your x, y, z here, the 2.7 would be like here, and the 10.3 would be, oh, say about here. And then you'd have to go up 75, which is going to be most of the way to the ceiling. And that's where these three planes would intersect. Now we can do a lot about the planes and stuff, and when we do multivariable calculus, we actually do that. We figure out what the normal vectors are and stuff, and then we can visualize them. We don't worry too much about that in linear algebra.
What are the normal vectors?
The vector perpendicular to the plane.
Oh, okay.
They're defined by the vector perpendicular and by any point on the plane.
Okay.
And it's easy to write down the equation in that case. But that's a different course, a different time. So you can actually do it. Okay. Take calculus 3, you'll do it. Don't take calculus 3, it'll always be a mystery to you, but you can look through that. Okay. Okay. So that's a process, right? Well, you know what? I'm really pretty tired of writing down all the x's, y's, and z's. I don't need them. Okay? All I have to do is make the convention in this matrix, and I'm going to put the equations in reverse order. First column be the coefficient of x, second column be the coefficient of y, third column is the coefficient of z. On the other side is what the number is they're equal to, and sometimes we put a dotted line there. Okay? And then the second equation is 5, 7, -1, 4. And then we've got 3, -5, 1, -5.
Didn't you put that one at the top?
Huh?
You put that one at the top. The one you just put down. You
I
put that one.
down what now?
You put that one down at the top.
I do that? Yeah, I did that. And actually, I'm questioning whether I want to reverse the order now. I'm gonna start a new video here because that one's getting long enough anyway.